It's okay? Okay. So as you can see, my name is Carbonell. I am from Paris, working in between Orsay and Saclay. And what I don't know is what you are, who you are. So you are PhD student, right? All of you. On what year? What year of the PhD? The second year? First? Okay. Mainly doing what kind of work? Experimental, theoretical? Theoretical mainly, okay, in the third year. So you have already heard about lattice QCD, all of you. So my difficulty was really to prepare the lectures because I don't know what you know. So I decide to assume, which is an assumption, that you know almost nothing. So I will go very, very slowly at the beginning. And if you are lost, you tell me. If you are it's too boring, you tell me as well, and we will adjust it. Another question is that some of you have to present some homework or some examinations or something like that, isn't it? So
Yes, but there will be
very few, because I prepare, as you asked me, some exercise, but
they do themselves also in a voluntary way, some exercise, and then they will ask you eventually.
okay. So what I put as an exercise is written in red. So it's up to you. You will, but in red in my, okay, I will tell you. I have two kind of exercise. One of them are, all of them are very simple. Some of them are simple manipulations to start. There are two which are really calculations. So one of them is you will see compute the QQ bar potential starting from scratch in your computer. You can do it's quite easy because it's only gluonic simulations. Another one is an exercise with to compute the scattering using lattice QCD techniques. So using the so-called Lusher formula. So these are the two exercises that you can start with, and we can end when they want, because it is impossible to do it during the week. So, but you have, or you can have my email, and we can continue to interact. So I start from the very beginning to introduce the formalism. So I take you where you are, where I assume you are. So the quantum field theory starts with a Lagrangian density. I will always use psi for the fermion fields and phi for the boson. So this is a generic. It can be quarks, nucleons, gluons or mesons. So this is valid for everything. And so we have to start with some Lagrangian density. The more famous one are the Klein-Gordon for the boson, which is, I remember, this one that everybody knows. For the fermion ones is the Dirac Lagrangian, which is a bilinear form. And the third part is some interaction. This is the intelligent part. So here for make application, which is a coupling between fermion and bosons. So for making the calculations, I will take the simplest model, which is very useful in nuclear physics, but it is also very popular now in the Higgs mechanism, the Yukawa coupling, which is, I will take even the scalar Yukawa coupling. So, which is something like that. It's the most simple interaction you can imagine between fermions and bosons. Okay, so I am using the covariant notation. I know which is 1 and minus 1. The V mu is always the contravariant, the usual coordinates. This is, and what else? Nothing. Well, the mu is the, which is, I always, and the gradient, the same. And okay, I think that's so. So I think you are familiar with all that. And the scalar product, of course, is V mu. Is an Euclidean one at the beginning, minus, is a, sorry, a Minkowski one. Just to start with that. So once you have the Lagrangian density, you can define the momenta. So the momenta with respect to a generic field is the derivative of the Lagrangian with respect to the zero derivative of the field. And this gives you the Hamiltonian. You can have the Hamiltonian density as a function of momenta, which is pi d0 a minus L. So this is very, very easy. You can check that for the Klein-Gordon, you can have the Hamiltonian will be simply a positive definite quantity. Important. For the Dirac, this is, you will have d dot gamma plus m. So the zero derivative disappears because this cancels the derivative, the temporal derivative here. So there is only spatial degrees of freedom. Is interesting. Okay, so with that, so how the dynamic is obtained? Is obtained simply, so the dynamics comes from a variational principle, which is that the action, so from the Lagrangian, we compute the action, and asking that the action is extremal, is an extremum with respect to the variation, we get the dynamical equations, which are for any field, if A is equal whatever you want, psi bar, psi, phi, whatever you want. Okay? So when you obtain that, it gives you the dynamical equations. If I always for an exercise use the Yukawa model, so I take the equation of that, I will obtain a couple equations. No. So this is the dynamical equations. Now is not the end. We have to quantify the system. It means we have to give some commutation relations at the beginning, at some time. So this gives us the dynamic, and we have to provide some initial time. We have to give some commutation relations. Otherwise, we are working with a classical system. And for the simplest case, this is, for instance, for the fuse and for the momenta is 0, and fuse with the momenta but this is only at t equals 0. So it is not written, but it is t equals 0. So we said at t equals 0, it goes like that. It means that we have to provide, to solve a situation in which, in the space-time, we have at each point an infinite matrix, which is an operator. These are operators now. I forgot to put the hot. The hot is, you will see, is time-dependent also. Sometimes yes, sometimes not. So, but this you can imagine at each point on the space-time, an infinite matrix which has to anti-commutate with a neighbor. This is impossible even to imagine. It has never been even tried that. And this is at t equals 0. And at t non-zero, in fact, we don't know. At t, for instance, if t in fact, to know that, we have to integrate the dynamical equation. We have to solve the problem. This is totally unknown. So we can say what are the initial quantization conditions, but when we let the time evolve, we are totally lost. This, in fact, is only known for the free case, and it's called the Pauli-Jordan function, some function which is known. But this is only for free case. For the interacting systems, we know nothing. So you can realize how this canonical approach to quantum field theory is something that had no future, in fact. It was used in a perturbative approach, but from our point of view, our aim is to solve a quantum field theory in the non-perturbative domain. This is an impossible task, a hopeless task. So that's why people start thinking other approaches. And this is the way we want. I forgot nothing. No. So you have to retain that this nice construction is only a theoretical, a lyric point of view, because even the commutation relation at different times are not known. How?
Near to your mouse.
Ah,
Questo. Okay.
can you hear me now? It's better. Ah, you were hearing nothing. Well, it was not so interesting anyway. Okay. So these are the first lectures, the first lessons on any quantum field theory book are really useless. Okay, so now we go a step further and we introduce it was the one, so here is the two, are the different representations of the theory, because of quantum field. So the most familiar is what you know. Everybody knows that the Schrödinger point of view and here the Hamiltonian and all the operators, all the other operators related to physical quantities, A, S, and so on, are time independent. But the states are time dependent. Okay, this makes the glory of Schrödinger and all your examinations on quantum mechanics. But it's not very adapted to our problem. This can be also, this equation is equivalent to this one. So we have some operator, the evolution operator, which make you a connection between the zero, t equals 0, in which we quantize, and any time. But it is not well adapted to quantum field. Why? Because in quantum field, the operators are the quantum fields depend on time. So this representation in which the operators are time independent are certainly not adapted for the quantum field theory. So we use what is called the Heisenberg representation. So instead of, this is the Schrödinger representation. And I'm going to start the Heisenberg representation. It comes from the trivial fact that you can always write that as you can always, so you can either put the dynamics in the state vector or in the operator. In the Schrödinger, you have made this choice. The dynamics is in the vector. Here is in the operator. So, in the Heisenberg point of view, the vectors in the Heisenberg representation, which will be the one we will use, almost everything, always, is something that is defined. It's always so trivial that I forgot. So the state vectors in the Heisenberg representation are defined according to that. Yes. And the operators in the Heisenberg representation are related to the Heisenberg, to the Schrödinger one by that. That's all. So this is This is really the representation we're going to use for the fields. So in particular, the field operators satisfy this kind of evolution. So in this representation, the states are static, and the operators evolve with respect to the time with the following equation. Which is called the Heisenberg equation. Two remarks. First, you can see from that, you can see the Hamiltonian in the Rödinger or in the Heisenberg representation are the same. It's the only operator that fulfills that. And you can see by direct insertion of that here, that the operators fulfill really this equation. So this is an exercise. Exo show that this fulfill that. Okay? This was the dynamical equation in which Heisenberg worked. In fact, is a particular case of much more general equation for the fields, which is if you take any field operator, then this is a more general. I forgot I here. Yes, this is a particular case of this Heisenberg equation of fields also, which is valid for not only for the time dependence but for the other variables. Okay, so we know this kind of evolution of the fields, and there is another one that we are also going to use. Which is the interaction picture, another interaction representation, in which both states and operator will evolve with time, but they will do it with the free Hamiltonian. So this is the so-called interaction picture is defined by H0 for instance for the Rödinger, okay? So they will evolve on time, and they will fulfill a kind of time-dependent, even if the interaction part is time-independent. Here we will introduce a time dependence, because this animal is in fact the interaction Hamiltonian in the interaction representation. So it's a little bit Kafkian. When you have your Hamiltonian, you have a free pair and an interacting pair. The interacting pair is here, but the interacting pair is time independent. When you use this interaction picture, what you put here is a time-dependent Hamiltonian, which is very unpleasant. But why is it interesting? Because the full Hamiltonian can be large, while the interaction can be small. And we have defined a representation in which things evolve with some small quantity. And this is very well suited for the perturbation theory. And this is the way in which all the quantum field theory, until the lattice calculations arrive, were performed, only perturbative. This is the trick. So, okay. So this is what I have to tell you about that. So I forgot nothing of important, no. This is true for the Hamiltonian and for any operator as well. You can always define any operator in the interaction picture, like that. And then you can define any operator in the interaction picture in the same way. In the same way. So I simply put that here. And the interesting thing is that EDT of that is, or I put here, is, the interesting thing is that any operator evolves according to H0. So the time dependence on these dynamics is trivial because is brought by is dominated by H0, the free case. The price is that the states evolve according to some time-dependent Hamiltonian, and this is very unpleasant. Okay. So the last thing I need is to tell you what is the evolution operator in this representation, which is like that. Okay. That's all. Well, now we are ready. Everything is okay? It's too easy? It's too trivial? No? You are already sleeping? How many of you are sleeping? No? I can go fast, but I don't... Can I? Well... So now you have, or you have to have, all the tools to attack things. So let's go to the 3, which is the S matrix. So with all that in mind, we know S matrix is by definition the relation between the state vector of minus infinity in the interaction picture only with the state vector in the, so imagine some collision, minus infinity, I go, I scatter, and I obtain some state, and the relation between these two states in the interaction is not true in general, only true in the interaction picture. And you can check that in the minus infinity and plus infinity, the states are free. So you can see that if H equal to H0, since state H free, there is no time dependence in the interaction picture. So this is a connection between two time-independent states. And of course, because the operator that makes the link between that and that is the U, you can define S as a limit, two limits, t plus infinity, t minus infinity of let me see, tf, ti, t initial, t final. So this evolution operator I wrote before in the interaction pictures, if you take these two limits, and these two limits exist, which is not so clear, give you the S matrix. Okay, so all the quantities you can compute in a theory, in the quantum field theory, are related to the S matrix. If it scattering, the poles of the S matrix will give you the bound states, the decays, everything. So if you have this animal, you have everything. Now, if you want to compute this limit, you will see if you take the Hamiltonian, it depends on the total Hamiltonian, there is no way. So, in this formalism, there is no way to compute this quantity unless you make a perturbative expansion. Then you can do it, and this is this is a Dyson perturbative expansion, which give you the S matrix as a, I don't want to make a mistake, minus y to the n factorial n, which is dt1, dt2, t product of the H, so the interaction Hamiltonian in the interaction picture. So if you do that, you obtain a perturbative expansion of the S matrix. All quantum mechanics has been done with this, and all the exercise you can get. But for us, this is not interesting, because we know that QCD, and in fact, not only QCD, let me tell you or remind you that all nuclear physics is highly non-perturbative. The coupling constant of QCD is alpha, is supposed to be very large, but it is of the order 1. Well, if you take the equivalent on any nuclear model, is of the order of 10. Nevertheless, you use a potential and so on and so forth, but because we don't know what to do. But so this is very often, this is an operator, because these are operators, often written in a compact way, which is how to say, it looks simple, but in fact is exactly the same. It is not simple at all, because it's not really an exponential. It's a t product of the exponential. So, and these exponential are not commutative. The exponents are not does not commute. So it's really it's the same way. It's as complicated as all the series. So there is. Now, so this was the situation before the lattice arrived. And now, how the situation is that we have to compute in a non-perturbative way an object, and there is no way to do it. And before going to Feynman, is just what is called the LSZ reduction formula, which is the last step until you die. This is a very interesting theorem, very general, which tells you that in fact any S-matrix element, so let's say let's call S a matrix element of the S matrix is operated between some initial and final state. So this is LSZ because it's Lehmann, Szymanczyk, and Zimmermann, okay? Tells you that in fact all that is in fact, well, maybe if I write you here, it will be more clear, I don't know. It tells you that this matrix element, so now I start here. In the simplest case of a scattering of P1 plus P2 going to Q1, two particles with momentum K1 and K2 goes into P1 plus P2 track. So this process, which is the simplest you can imagine in the scalar theory, so no fermions because it's complicated for nothing. So this S-matrix element, this is nothing, this is nothing, this is nothing. This is the interesting thing. It's simply a vacuum expectation value of products of fields. It has nothing to do. So I have even not to think. It's like my GPS. I can drive being idiot. Here is the same. I can forget about everything, about all what we have learned in quantum mechanics. And if we learn how to compute the product, the T product, but the T means the, how is called this? The time what? Time ordered, okay, but this is a stupidity. You have to order the times from plus to minus. Forgot about T. If I know how to compute products of fields, vacuum expectation value, I have everything in my theory. This is a good surprise. The rest is stupid. Z is some constant, normalization constant, M is the mass. These are the free propagators of the two incoming and outgoing particles, the free ones. Not free because I have a normalization, but this is the S matrix. So this is so I make you. This is the S matrix. Sorry. So the S matrix. Yes. So if I take the S matrix, I divide by this factor, I can compute it on this way. So because I tell you that S was here. In fact, the real... Sorry? Where are? In the denominator. Yes, sorry. Sir. Here is a square, thank you. And this is S between the initial and final state. So I put that here. I can compute the S matrix element. This is why. Compute the S matrix element. If I take this factor, I put it here, and I know how to compute this average value of products of fields. So you can forget about everything except about that. And this is the way how to compute them. How to compute that? So these animals are called the green functions. In this way, if you don't have the T, it's called the Weightman functions and blah, 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 but it's the product of fields. So that's good. We can be stupid and do physics. Now, how to do it? And here comes the Feynman path integral formulation. Formulation of QFT. In fact, well, yes, in fact it tells you that. It is already written here. It tells you that we know how to compute that. The vacuum expectation value of products of fields can be computed in this way. These are the classical for the scalar theory. Eh? So here I put d phi. And it means that we have not to integrate any equation, we have not to solve the field situation on the space, we have simply to compute vacuum expectation values in this way. Now, this way is very dangerous. Well, let me just complete, and Z is the same without that. So Z is simply, and this is the action, which is obtained with the Lagrangian. Okay. Now here is really very tricky. First, because on left are the real fields, solution of the problem that we don't know how to solve. While here there is no hot, but in fact it's a dummy variable. It means all the classical fields which are compatible with some boundary conditions. So in fact is put whatever you want here, everything which is classical times something which is known, and you will obtain the solution of the interacting fields that we don't know. So it's really something that is very, very shocking. Now, what is the relation between that and that? Here is a dummy variable that you have to take all the fields, but nevertheless, there is some relation. So this relation is not very easy. It will take me 1 week. No, it will take me 6 months to learn it and 1 week to explain you, because in fact these are representations of the field. If you want, they are coordinates of the field. In the same way that when you have that, you have a set of eigenvalues. In the same way, but not exactly, you have some states. And here are the field, the operators, and these are some eigenvalues of the operator which represents the field. It is not exact, because in fact they are the coherent state, which is more complicated, but you can have this a kind of guess of what is the relation between this and that. So they are representative of the field, coordinates of the fields in some basis, which is called the coherent state basis, but which is really tricky. So this is very fast written, but it's full of traps. I mean, in each line there are 10 traps. In each symbol there are 10 traps. Now, this is true, and these are real numbers. They are numbers. So I can put it in the computer, while that are operators. If I take a theory with fermions, so if I have, well, this is not only true for the product of fields, it's true for any operator I can build with the fields. It's the same. I put the same. Here are numbers, not only for this product, but for everything I want. Now, this is for the simplest case of the scalar particles. But QCD is made of quarks, so we have to introduce the fermions. And how it changes if we use the fermions? In fact, I will make something which is very very unpleasant for you. If I have fermions, what change? It changes that here I have psi, bar, psi, and some scalars as well. Then I have to do exactly the same, but multiply psi bar operator which will depend on that. Okay? And here now there is, at the same time, the problem and the miracle of lattice QCD is the fact that these variables, the fermionic variables, these coordinates of the fermionic fields in the coherent states are not numbers, are what is called the Grassmann variables. So they are numbers that anti-commutes. But the computer is stupid, it doesn't know how to deal with that. And in fact, the miracle of the lattice QCD is that this part, which deal with Grassmann variables, is performed analytically. So, if we take, how to say it, first, I will put the result here. I have to split the action. The action is a boson pair plus a fermion plus interaction. But this fermion plus interaction, you can see in the Yukawa model, for instance, and everywhere, that is always written as a bilinear form, some operator is a bilinear form between the fermion fields. Okay, so if I split this action in this pair plus this one, I have the following. I will have the phi, and then O fermion plus interaction times boson. And this part, which contains all the fermionic variables, is analytic. So we know the result. And there is no any need to compute what, in fact, we couldn't compute. So I will give you the result with that. So keep in mind that each time we have a fermionic variables, the integration over the fermionic part is known analytically. Why? In fact, because the part of the action that is concerned by fermions is the fermionic plus the interaction, and is a bilinear form. So this is a bilinear form on the fields. And this is, so I will give you the only two results we need. Well, I will not give it right now because I will give you the result later. But you keep in mind this, that in the Feynman path integration, the fermionic part is analytic. And what remains is this analytic result multiplied by, some of the scalar fields. And that, we know how to do it. We know how to do it, and the last point is that, in fact, due to this imaginary number, this integral is extremely oscillating, and even if we know how to compute, there is no way to compute because it doesn't converge. And this is the reason why we have to do two things. First, to discretize the space-time, and second, move into the imaginary time, change the metric. From the Minkowski, the original metric in quantum field, to the Euclidean one. So, this is the Euclidean QFT. So in fact, we take any Green function or Widman function, x t1, x1, tn, xn, which is defined as the vacuum expectation value of the product of fields. Now I forgot the T, and I call it Wigman, but it doesn't matter, okay? So this, you can, if I put here the real axis for time, you can imagine that as a function which takes some values in T1, T2, Tn, okay? If I know how to, in the Minkowski theory. And what we are going to do is to compute these quantities, not here, but here, at Z1, Z2, Zn. This is the proper way to move from the Minkowski to the Euclidean quantum field theory. Now, of course, when we do that, we can, if we do it, it's because, for instance, the action will become, I times the action will become real, but some quantities will remain unchanged, but of course, we will know the theory here, and when we do that, this rotation back to the origin is not always possible, and we lose things. So we are not saying that we are really, is strictly equivalent formally, but once we do that, this way, we cannot do it. We can do it if we know a complex variable which is known analytically, and we replace z by I don't know. But if we make a solution, a numerical solution, we lose some information. Another thing is that when we go from here to here, what time?
We have another 5 minutes.
5. We have to be sure that there are no singularities that are crossed. And this is not obvious at all. So I am telling you what we are doing. I am not telling you that we have to write to do it. It's a very delicate problem. I can give you a list of authors that work on that. That starts from 54 with Vic Giancarlo, right? In another framework of Bethe-Salpeter equation. But it's really a tricky thing. So it's doubly tricky. First, because we cannot return easily. And second, because it's not clear that we have the right to do it, because we can cross some poles or things like that, and then this analytic continuation will be meaningless. So in practice, and I will, it's exactly what I supposed to do in the first lecture. In practice, this is done by changing the metric. So instead of x0, x1, x3, we put the Euclidean. Instead of the Minkowski coordinate, we take the Euclidean, which are x1, x2, x3, and x4. So the time, I will put it at the end. And the relation is that x4 is e time x0, which is the time. x0 is time. I put x now because it's... So, but I would like to insist that it is not merely a change of coordinates. Of course we will change the coordinate to adapt it to the new situations, because we want to use, we want to use another set of coordinates for different things. So, and when you do that, of course the volume element in Minkowski is related to the volume element on Euclidean. The gamma matrix of Dirac, instead of being 2G mu nu, are simply 2 delta mu nu, delta functions. There are some changes. I mean, gamma Euclidean, gamma 0 Euclidean is the same than gamma 0 Minkowski, but gamma vector Euclidean is not the same, is minus e. Gamma vector mean 1, 2, and 3, the x, y, and z, okay? So there are things like that. The most interesting thing is that, for instance, the Klein-Gordon Lagrangian in Minkowski becomes minus So this is minus Lagrangian in Klein-Gordon, minus. For the Dirac is the same. So let me finish with Klein-Gordon. And the action, the action in Minkowski for the Klein-Gordon becomes I times the action in Euclidean for the Klein-Gordon. So when I multiply I times S, I have minus S. So the action exponential ES becomes exponential minus S Euclidean, and S is definite positive, which is much more interesting. And the same happened for Dirac. For Dirac, L Minkowski, the Dirac, will be now, in fact, is will be minus L Euclidean the Dirac, and L Euclidean the Dirac is now no I, no longer I, is simply gamma mu Euclidean d mu Euclidean plus m. So it's much more easy. So the Dirac equation is not minus e gamma mu d mu minus m, is like that now. And also, Minkowski Dirac, Euclidean Dirac. I think I have to stop now. Yes? Okay. So we will enter into the beef of the subject tomorrow morning if you are still alive. Thank you.